The buck converter is a step-down voltage regulator, and its core components include a switch, diode, inductor, and capacitor. The power supply output is directly connected to the switch, with a diode in parallel with the front end of the inductor. The capacitor and load remain unchanged. When the switch is closed, the circuit becomes conductive, and the diode is cut off. The current flows directly through the inductor, which stores energy and supplies power to the capacitor and the load. Since the inductor resists changes in current, the current gradually increases, and the output voltage rises as well. At this point, the output voltage waveform looks like this. As the voltage increases to around 5V, the switch needs to be opened. The inductor generates a reverse voltage to continue supplying power to the load, with the current flowing through the diode to form a loop. The capacitor helps maintain a stable voltage for the circuit, preventing a sudden drop in current. As the current in the inductor gradually decreases, the voltage at the load decreases as well, and the corresponding voltage waveform looks like this. Before the voltage drops to zero, the switch closes again to start a new charging cycle. The output voltage waveform continuously fluctuates, and the average value of this waveform is approximately 5V. This is controlled by the switching duty cycle, which is the ratio of the time the switch is closed to the total switching period. For example, to step down the input voltage of 12V to an output of 5V, a duty cycle of about 42% is needed. This means the switch is closed for 5 to 12 of the time and open for 7 to 12 of the time. Since the switching frequency of a buck converter is very high, typically using fast switching components like transistors, the circuit can switch at microsecond speeds. This is the basic principle of the buck step-down converter.